Here we're going to start talking about inverses of matrices, and the best thing about this first part is that we're not even going to learn how to calculate them yet. We're just going to see what they are and what we can do with them, and maybe how to spot them even if we don't know how to calculate them. First thing we have to do is look at why we need them in the first place. How do we spot matrix inverses, and then how do we use them when we have them? Later on we'll learn how to actually calculate them. So here's the problem. There is no such thing as matrix division. We've done matrix addition, we've done matrix subtraction, and we know how to multiply two matrices together, but that's the end of the line. There is no such thing as matrix division, which seems sad, but if you think back to numbers, it turns out we can get away without division when we're dealing with numbers even. We just have to change the context. So for example, here's A divided by B. It's a division. If B isn't 0, what we can do is think about the division by B instead as the multiplication by the reciprocal of B, or the inverse, of B, and we have our own special notation for that, which is B with an exponent of -1. So with inverses, even with numbers, we actually don't need to worry about whether there's division, because division and multiplication by an inverse, same thing. Not all numbers have inverses. Well, 0 is the only number that doesn't have an inverse or a reciprocal, but still, we have notation for inverses with that -1 exponent. And when inverses are around, we can use them, for example, to solve the equation Cx equals D without division. If C isn't 0, then we just multiply both sides of the equation by the inverse of C. Now I'm going to do this painfully long. I'm going to show you the grouping of C inverse with C because we have to remember what the job of the inverse is. The job of the inverse of C is when you multiply the inverse of C with C, you get 1 back, and then that 1 times x is just x. Right? That's the job of a numeric inverse, is you multiply it by the number that is its partner in either order, and you get 1 back. Matrix inverses are going to work the same way. We will generally use capital letters instead of lowercase to represent matrices. Now the facts are, not all matrices have inverses. With numbers, there's only the one number, 0, that doesn't have an inverse, but with matrices, there's a bunch of matrices that don't have inverses, and so we have to learn how to test. The inverse of a matrix will use the same -1 exponent, and we can use inverses of matrices to solve matrix equations. For example, this AX equals B matrix equation, if we want to find out what X is, we can multiply both sides of that equation by A inverse. Okay, remember the job of inverses is to produce, for numbers, a 1, and so the job for matrix inverses is, with multiplication by its partner, to produce the identity matrix, which is the matrix version of the number 1. So solving this equation, AX equals B, we can multiply both sides by A inverse. Let's be very careful to group the inverse with its partner properly, because that multiplication produces the identity matrix, and remember what the identity matrix does. I times X will just be X. And so with the existence of a matrix inverse, we can solve a matrix equation by matrix multiplication, which means we can solve systems of linear equations by matrix multiplication as long as the coefficient matrix has an inverse. Okay, so we're not going to learn how to calculate or compute the matrix inverse yet, but we can still learn when we have one, and the way we do that is to remember what its job is. And when we have a matrix and its inverse, that inverse relationship works both ways. The A inverse, A to the -1, is the inverse of A, and A is the inverse of A to the -1, just like 2 and 1/2 are inverses of each other. So 3 matrices here. There's a pair of matrix and its inverse in there. How do we tell which is which? Well, we try some multiplication. So it turns out that, okay, that's my shortcut. You can pause this. You can go back if you need to practice with matrix multiplication. Go back to the previous screen. Look at those matrices, grab A and B and multiply them together, and it will turn out that A times B is the identity matrix. If we start the multiplication of A times C, the very first entry we get is a 5, which is not going to be the identity matrix, so with one calculation we know that A and C are not inverses. A and B are likely inverses as long as B times A also produces the identity matrix, which it will, and so A and B are the inverses of each other. And there's some notation we can use to write it. So using inverses, let's solve this matrix system. We write it in its matrix format. which is ax equals b in shorthand. We have the coefficient matrix on the left, the right-hand vector on the right. We want to learn x and y and z. And so we can multiply both sides of this equation by the inverse of that coefficient matrix as long as that inverse exists. Okay? Now, because of the matrices A and B from that previous example, I was being sneaky, and I already provided the inverse of this matrix, 1, 2, 3, 2, 5, 3, and 1, 0, 8. It happens to be this other matrix shown on the screen. If you don't trust me, go back and look. You'll also learn how to calculate inverses later on. So knowing what that inverse is, we can put it in play. So instead of ax equals b, we have x equals a inverse b, and a inverse b is right here. And when we carry out that multiplication, we get the values for x, y, and z. So solving that system of linear equations was nice and simple with the inverse in play. The problem is going to be that if the system isn't square, the coefficient matrix won't have an inverse. If the system is square, it's possible that the coefficient matrix might not have an inverse. And so we still need to know how to solve equations by elimination because we're not always going to have the inverses available. Next up, how to calculate the inverse.